My name is Dan Guido. I'm the CEO of Trail of Bits. If you all don't know what that is, how do I go? There we go. Okay, cool. So who the heck is Trail of Bits? We're a software security research and development firm that I founded about 10 years ago with a couple of friends. At this point, we're kind of like a large security company. We do a whole bunch of things under one roof. We have a group of people dedicated to doing long-term US government-funded research in low-level software, compilers, modern cryptography. We have an engineering team that tries to address problems in software by writing more of it. We're doing a whole bunch of really cool stuff on ecosystem security for Node.js, for the Python Software Foundation. We are writing code that helps people create software bill of materials. We're writing code that prototype security products. Sometimes people hire us to actually develop and prototype security tools and products that they rely on. And then we also do security assessments, which is really what all of you here are to talk about. We review the security of high assurance code, not just in the blockchain space, but anywhere where the consequences are high. So think like software that runs on satellites, on cars, on planes, cryptographic software, the backends of cloud systems, whether they're using cloud native software or they're a cloud provider themselves. And that's what sort of drew us to blockchain security. It's another example of high assurance software. So what I wanted to talk about really quick was how Trail of Bits thinks about blockchain security and how we kind of relate this to security in other fields and why we think it's a little bit different on blockchains and kind of like how that's evolved. So this is going to hopefully provide some perspective that I can give to you all. So as you know, blockchain security is a little bit of a tire fire. There's these tiny programs, these little finance bots. Really, I would call them finance pinatas, and they keep sort of getting hacked, right? The main language is Solidity, which is kind of like JavaScript, but worse. And the community around us, like while everyone here, I think, is really into security, not everybody is. We've got a compiler that sometimes introduces correctness bugs into code that people write. And we gave an entire talk about this called The Anatomy of an Unsafe Programming Language, for which a video is online. So, and to give an example of how some people in the community think about security, I copied this quote from a Medium article down below where people just forget to do audits before they launch. No big deal. I think that was important, but we didn't really care that much, so we just launched, right? If you think it can't be that bad, I'm sure that now going through the Securium training, you all know that this language is filled with footguns, right? Like you've got this loop up here, which looks like a really standard, computer science for loop, whatever. But because of the way Solidity works, it turns into an infinite loop if there's greater than 256 elements, because I is 8 bits, and it gets declared as a var instead of a specific type, right? And then in the second little example here, anything to the 0 power is 1. So 256 to the 0 power is 1. Like a real compiler would constant fold that out. And the proof here is that there's been like $10 billion worth of money stolen on the blockchain, right? It's ridiculous. The language itself reinvented dozens of problems that were eliminated from modern languages. Like every modern language made in the last 10 years does not have these bugs. If you think about Go or Swift or Rust, none of them have exploitable null dereferences, right? So it looks like a massive step backward when it comes to security. So your expectations are that, well, there's going to be tons of easy bugs. That's what you would expect, like given the setup here. That analysis would be really tricky, that EVM is this weird stack machine, the language doesn't make a whole lot of sense. They changed the order of operations, right? Like how, why, I don't know. So you would think that confidence in especially smart contracts on blockchains would be impossible, right? Regular software is bad enough, but now we've just like given you all this extra stuff to deal with, so it would be terrible. But the reality is that from TrailofBits' perspective, I can see across many different industries and work in many different industries. And the blockchain part of it is kind of leading it when it comes to security. It's really backwards. And it took me a while to really figure out why. Clients come in the door with specifications and property tests. People routinely use formal methods like symbolic execution in order to evaluate their code. And in fact, symbolic execution is a competitive space. Right? There are companies out there where it's extremely important to them to have like the best symbolic executor, and people are really interested in seeing which one's better, right? It's wacky. So you'd ask like why that is, and there's a trope that people think that it's because of incentives, right? Like it's not true. That's absolutely not true. That you need to be right the first time, well, whatever. There are a lot of people that have incentives to write secure code. Right? Companies that make autonomous driving software have an incentive to write secure code. Apple has an incentive to write secure code. They ship out 1 billion iPhones, and there are heads of state that use it. You can just read the news about NSO Group, and their target list of the week that Citizen Lab finds. So there's a lot of people that have a lot to lose, and there are a lot of people that are investing hundreds of millions of billions of dollars more into security than anybody in the blockchain space ever could, right? Mega corporations like Google will literally invent and develop their own programming language to help their developers write secure code, and they won't get as secure as blockchain software is. So to step back, there's this joke about a dairy farmer that's trying to keep up with the agri-conglomerate down the road. And he asks a physicist for help. And the physicist comes back a few weeks later and says that he has a solution. Physicist has a solution, but it only works on spherical cows in a vacuum. That is what makes this field special, is that Ethereum really only supports spherical cows. That all this stuff that has been developed theoretically, that has trouble applying to real software, actually works extremely well on blockchain software. So what we see is that all this software testing research that we would like to apply actually works on platforms like Ethereum because of the extremely limited runtimes that we need to analyze to get there. So let me take a step back just for like a minute and talk about what is a program, because I think it'll help put this in the right frame of mind to think about software testing and verification. So what's a program? So this is from a keynote that I gave. No one's recorded it yet, so no one has ever seen this. It's not online. But let's pretend that a program looks like this on the bottom left. There's some input space, and the points in it represent different inputs that you could make, and the inputs get fed into a state machine, and that state machine bounces around a little bit until it finally terminates or not, right? So now, if you define a program like that, software security is essentially two questions. Is one, what inputs define bad behavior? So that's like input-driven kind of testing. And then when is a state bad? Are there places in the state machine you don't want to be? And the first one would be software security techniques like fuzzers and symbolic executors and other kinds of automated testing. And then number two would be things like address sanitizer or inserting asserts that would help you find out those sorts of issues. So let's talk about number one and just work through what the options are for that sort of thing. So the simplified version of security in this little model that I've made, you've got three different options for securing a piece of code. You've got actually, you've got two options. You've got the starting space, which is unrestricted input. So you can see there's a bunch of like, little, there's a bunch of little dots that have been made into that input space. And those are things that you've tested maybe with like unit tests, right? You're testing one field at a time. So you're just going to pop into, random little spaces in the grid. You can try to restrict input. So obviously it's easier to test across your entire code base if you just have less stuff to test, right? So you can get that. You can get there with like a typed language. You can delete code. You can do privilege separation, and you can restrict input. And the other thing that you can do is you can try to test more. So those are your unit tests, your fuzzers, your property testers, and that's sort of what it looks like on the right. Is you get these stripes if you have like some sort of property that you've tested. You might get a lot of little random dots if you're doing a fuzzer. So most people, as they go through this progression, they all kind of escalate in maturity from this starting space, which is that, well, I'm just going to try really hard. I'm an expert developer. I've studied the language really hard, and I've had a bunch of people code review my pull requests. So, I'm just going to think really hard. I'm not going to introduce any bugs. And this is absolutely insane, right? Like the human brain is not a computer, and there's absolutely no way that you can think of everything that you don't know in order to test it effectively like that. The next phase is you try a few inputs, right? Like, oh, well, at least I'm going to have 100% unit test coverage, and that's going to keep me safe, right? That's the next space that people land. And it's considerably better than the step before that, but it doesn't really work because most things aren't unit tested. Programmers don't know all their unknowns. When you look at the regular software industry, this is the state of the art. When we talk to clients outside the blockchain space, most of the time, they're going to be extremely proud that they have unit tests. That's like a thing that you can use to list on your job ads. Like, hey, come work here because we test our code. Right? Developers are very proud of that. Some people make it to phase 2, which is trying lots of random inputs. So eventually they figure out that, oh, okay, I don't know everything I don't know. So let's try to write a fuzzer. And nobody is ever upset after they run a fuzzer. Nobody runs a fuzzer and is like, wow, that sucked. Right? Like usually it's magic. It's like, oh my God, our Lord and Savior quick check or AFL or libfuzzer or whatever. These techniques are unreasonably effective, and all they're doing is popping random dots into this input space. It's not even like driven in any sort of direction. So fuzzing in the regular software industry is starting to gain acceptance. And then the ultimate place that you'd want to be is you'd want to actually test all the inputs, right? You want to get to a place where you can test everything. It doesn't give you perfectly correct software, right? Like who verifies the verifier. Sometimes like the little thing on the right is you find that there are inputs to the program you didn't even know existed, like from the environment somewhere or whatever. So I just drew a little extra dot that's like hanging out on the right. And most people reject this as impractical, but when it works, it's incredible. So what we see is that everybody's sort of at phase 1-ish, right? Like they're writing some tests. And phase 2 is next level. We actually did a really funny project on our blog called Fuzzing Like It's 1989. You'd have to excuse me. I have a really bad respiratory thing. It's not COVID, but it feels just as bad. We resurrected the original fuzzing paper from the University of Washington in 1989, got the fuzzer compiling again in like modern C, and then ran it against the targets they ran it against in 1989, like the modern versions from Linux. Or now Linux, because it didn't exist in 1989, but the same utilities. And it finds most of the same bugs. Like we didn't even correctly patch and eliminate all the bugs that the world's first fuzzer could find, right? And then phase 3. So like if you actually do apply fuzzers, you almost never make it to phase 3. So what the blockchain got right in this case is it actually helps us write testable code. Normal software is untestable. It has poor abstraction boundaries. The environment is mutable. There's global mutable state. There's all kinds of reasons why it's hard to write testable code. But on the blockchain, I already blew my joke here. Brown cows make chocolate milk. Do spherical cows make Dippin' Dots? So like, how is it different on the blockchain? How it's different is that every state's a transaction. So it's really clear what is happening. The transactions are atomic. The code is tiny. It almost has no control flow. A little screenshot on the right shows the output of a tool we wrote, a disassembler called EtherSplay. And that's a program. That's it. This sort of structure enables us to apply a lot more rigorous analysis techniques and automated testing techniques than it would on like Internet Explorer, right? The input size is expensive. We pay per instruction executed. Termination is necessary. So like, these are the incentives that I think about that matter. Not the code is law thing. These incentives, the fact that anytime state updates, we're looking at transaction data that's very small. We have clearly defined state variables that are also small. The input size, state variables, instruction traces are all tiny. This is a manageable problem for advanced techniques to apply to and not run out of steam. So the big picture is code correctness tools actually work here. And we found a way to make the developer experience basically just /find bugs. And most people love it when they are able to do that. When they download a tool like Slither, the devs that come over from this field, and hopefully that some of you, are blown away at sometimes how easy it is to verify the code that they're working with. Now, Solidity is not exactly help here, but it is getting better. And what we found is that this, like, in normal land, in like traditional security, you would say that the only way to write secure code is to have a safe language with safe frameworks, right? That's like a common refrain for people. But what we found in blockchain land is that actually testability trumps the language security, the compiler security, the framework security. Like, all that stuff doesn't matter. What matters more is that you can rigorously test something. So, oh, there it is. Yeah. So this is the ideal body. You may not like it, but this is what peak performance looks like. So you're a little tardigrade here. This is Ethereum. So how does that work in practice? Couple notes for what projects with Trail of Bits look like. So on day one, we usually exert extraordinary effort to make sure that we can build code. Now we have to exert crap ton more effort. Sorry for being so vulgar. I'm not quite awake yet. We have to exert a lot more effort in order to do that with software we get in other industries, because the build systems aren't so portable, and there isn't just like one developer environment that people use, whereas instead there's just one blockchain. So we don't have to worry about things like developer libraries, like what version of Windows you run on. Like, none of that matters because there's one blockchain. So it's very easy for us to build the code. The next thing that we do is Trail of Bits takes a hybrid combined approach to doing security assessments. We are going to review the architecture and design and perform a manual security review on one hand. And then in parallel, we're always extracting properties, extracting client goals, extracting specifications from the code that we write, and then encoding them as machine checkable invariants, as properties that our tools like Echidna or Manticore or Slither can evaluate. And that produces these weekly reports and code updates that you get. You're going to have to excuse me a second. I'm like dying over here. Okay, let's see if I can keep it together for like 2 more minutes. So we try to give invariants with programmatic tests for every single engagement that we work on. Property tests cover a lot more, sometimes all possible inputs if we're using them right. So we want to deliver the ground truth, right? If you have 30 defined security properties, we can use a fuzzer or a symbolic executor to evaluate them on every single commit and give them back to you to run in your CI. That's the state that we want to get our clients to. So really short case study. We were taking a look at primitive finance. Really one of the, we like them, let's just say that. So we needed to ensure the correct operations of a DeFi options trading protocol, right? It allows users to add, remove, and swap funds. It's going to be trustless, so completely immutable. There's no owner privileges. And the client knew that ahead of time, knew what the goals they wanted to get to were. They knew what the specifications for the system were, and had to ensure that there was no loss of user funds. So, again, we follow a pretty straightforward process here. Step 1, find security properties. There's a lot of different places you can get them from. You get them from speaking to the developer. We might interview people from the team. Hey, what were you trying to do here? You'd read the documentation. If the specs aren't discretely defined, then sometimes they're explicitly defined. Sometimes they're implicitly defined by reading things like code comments or in between the lines of various portions of the white paper. And then we define them programmatically. So in this case, we want to create an end-to-end testing suite, which we do with Echidna. We want to get code coverage of all the functionality that hits unsafe code. Oh, nope, that got copied from somewhere else. That was for a Rust project. But in this case, we wrote out 57 properties that detect deviations in a lot of the mathematical assumptions that the primitive finance people made. And then step 3 is, once we've got some of those defined, those 57 properties, we want to run them on every commit. So for that, we have GitHub Actions associated with all of our tools. In this case, you can see the Echidna action that's up on the GitHub Marketplace. So we collaborated on a pull request back to the primitive finance people to add them to their CI. And now it fails the build if somebody tries to add new code that violates one of those properties. So here's an example of some of the mathematical formulas that they wanted to evaluate and that we were able to encode into Echidna. It's reasonably complicated stuff. So we can prove some high-level properties about the code. It's not just like integer math, right? We can do things that are meaningful to the software developer, things that are meaningful to the business owner of the system, which could define like, hey, does my code still conform to what I described in the paper? And then this is what the output looks like. In our reports, we always write out the list of properties that we were able to develop, the tool, the evaluation technique that we used. In this case, it was all fuzzers. And then the results. Did we find any bugs with that? And frequently we do. So in this case, this is just a screenshot of a portion of it, because remember, there were 57 tests. But we found in this little screenshot 3 unique bugs based on this kind of verification-driven testing approach. So that's sort of at a high level how I think about blockchain security and why Trail of Bits uses the approach that we do. I just wanted to say that, well, first, I'm sorry I couldn't be there. I really wanted to go out and hang out with you guys in Amsterdam. But if you'd like to get in touch with me, you can always email me, dan@trailofbits.com. We've got a lot of great resources on our blog, and we've collected all of our blockchain-specific tools for Trail of Bits under the GitHub organization Critic. So if you're not already familiar, I would encourage you to go spelunking through that GitHub org, because there's all kinds of really fun stuff that you probably haven't seen yet. And that's it. I think I'm probably over time for questions, but feel free to reach out to me on Twitter, on email, or whatever. I'm available. Thanks.